I had a bit of an existential moment this morning on the way to the studio.
Oh, yeah. Too much coffee, or maybe not enough.
A bit of both, probably.
Yeah.
But no, I was just walking down the street, coffee in hand, looking at the pavement, the brick buildings, the trees, and everything felt so incredibly solid.
Right.
You put your foot down, the ground meets it, it's not moving.
Yeah.
It feels like this permanent stationary stage that we act out our lives on. It's intuitive, it's obvious, it's terra firma. Right?
It is the ultimate illusion, isn't it? The stability of the ground beneath our feet is probably the most convincing magic trick the universe plays on our senses. We're biologically wired to assume the ground is static.
And that's what we are here to dismantle today. Because the reality, and this is what we're going to unpack, is that we are actually standing on a wobbly, spinning, slightly squashed rock that is hurtling through a violent vacuum. If we could actually feel the physics of what the Earth is doing right now, the sheer velocity and the forces at play, I think we'd probably all be screaming.
We'd certainly lose our lunch. Our inner ears wouldn't know what to do with that information.
So today we are doing a deep dive into the spinning blue marble. But we aren't just talking about geography or memorizing capitals. We are looking at the heavy-duty physics that shape our reality. We're talking gravity, the geometry of space-time, the terrifying silence of the void, and the destiny of the planet itself.
And we're going to use that as a launch pad for a really specific, really terrifying thought experiment.
Exactly. What happens if the spinning just stops?
It's a scenario that keeps physicists up at night. It sounds so simple, but the cascading effects are, well, they're apocalyptic.
We're going to get right into that. To guide us through this, we have pulled a stack of absolute heavy hitters. We're not messing around with Wikipedia entries today. We're pulling from Neil deGrasse Tyson's Astrophysics for People in a Hurry, Brian Greene's Mind-Bending the Elegant Universe.
A personal favorite.
Oh, absolutely. Stephen Hawking's The Universe in a Nutshell, and of course, the legendary Carl Sagan's Cosmos. And we've also got some fascinating insights from Lewis Dartnell on how the Earth's very geology actually made us who we are.
These are the titans of explaining the unexplainable. They make the incomprehensible, well, slightly more comprehensible.
Right, so the mission is simple, to deconstruct the Earth. We want to stop seeing it as a place and start seeing it as an object, a physical object, subject to forces so massive they bend time itself. So let's jump right in. Let's start with the shape of the thing we're standing on.
Let's do it.
Okay, so pop quiz for you listening. What shape is the Earth?
Well, if you look at the globe in your kid's classroom, or even those iconic blue marble photos from the Apollo missions, the answer seems completely obvious. It's a sphere. A perfect round ball.
It's the emoji for the planet, a perfect circle.
Exactly.
And here is where it gets interesting immediately. Neil deGrasse Tyson makes a huge point of correcting this. He points out that while round is a good approximation for a casual conversation, it's physically impossible for the Earth to be a perfect sphere. And it all comes down to the mechanism of how it moves.
It's the rotation. It's the spin. We intellectually know we are spinning, but we just don't feel it. The Earth rotates once every 24 hours. Now, that sounds slow when you say one day, but the Earth is massive.
It's huge.
It's huge. And to make that full rotation happen in that time frame, the land at the equator has to move at about 1,000 miles per hour.
1,000 miles per hour. Let's just sit with that for a second.
Yeah.
That is faster than the speed of sound. So right now, if you are sitting on your couch in Quito or Singapore, you are actually moving faster than a bullet just by sitting there.
And all of that speed, that constant motion, it creates a massive centrifugal force. Tyson uses a great analogy here to explain what that does to a planet. He talks about the hamburger effect.
I love this because it's so visual. He says whenever he eats a hamburger, he thinks of Saturn.
It's a vivid image, isn't it? Basically, you've got gravity, which is this immense force trying to pull everything into a tight, perfect sphere. It pulls equally from all directions toward the center. That's why raindrops and planets tend to be round. It's the most stable shape.
The path of least resistance for gravity.
Precisely. But that spin, that 1,000 mile per hour spin, is pushing outward, specifically at the equator. It's fighting gravity. It's trying to fling things off.
Like when you spin pizza dough. I always think of that.
Exactly like pizza dough. As you spin it, it flattens and widens. So the Earth gets squashed. It's wider at the equator than it is from pole to pole.
It's an oblate spheroid.
That's the technical term. It's a chubby sphere. Tyson notes that the pole-to-pole diameter is smaller than the equatorial diameter by about 26 miles.
Which, in the grand scheme of things, doesn't sound like a huge number when you're talking about a planet that's 8,000 miles across. But it has real-world consequences, right?
It absolutely does. It completely changes how we define the highest point on Earth. We all learn in school that Mount Everest is the highest mountain above sea level, period. End of story.
Right, highest peak.
But if you define highest as the point farthest from the Earth's center, which is a perfectly valid way to measure, Everest loses the title.
Because Everest is at a mid-latitude. It's not on that bulge.
Precisely. The title actually belongs to Mount Chimborazo in Ecuador, even though it's shorter relative to sea level because it sits right on that bulge, the fat part of the Earth near the equator. It gets a free ride. It bumps it out further into space than the peak of Everest.
That is a great cocktail party fact. You can win some bets with that one.
You definitely can.
But let's pause here and do that thought experiment we mentioned. This is where it gets scary. We are spinning at 1,000 miles an hour at the equator. That spin is creating this bulge. What happens if we just stopped?
Okay, so you have to define stopped. This is crucial. Do you mean we hit a cosmic brick wall and stop instantly? Or do we slow down gradually over, say, a few decades? Because the physics are wildly different.
Let's go with the dramatic one first. The instant stop, the cosmic brake check.
That is the Michael Bay scenario. It's total, utter devastation. See, the solid part of the Earth stops, but everything on the Earth has momentum.
Newton's first law. An object in motion stays in motion.
Exactly. The atmosphere, the oceans, the buildings, you, me, every tree, every car. We're all moving at 1,000 miles per hour due east. If the ground suddenly stops, the atmosphere doesn't.
So you would have 1,000-mile-per-hour wind? Is that what that means?
Instantly. It would be a supersonic blast wave. It would be a wind so powerful it would have the abrasive force of a sandblaster. It would scour the surface of the planet clean. It would rip buildings off their foundations, flatten forests, and essentially pulverize anything standing.
In the ocean.
The oceans would retain their momentum too, so you would have mega tsunamis, miles high, crashing eastward across the continents at close to the speed of sound. There's no barrier that could stop that. It would wash over everything.
It's effectively a blender. A planetary blender.
It's a global reset button. Life might survive deep in the ocean or miles underground, but the surface would be sterilized.
Okay, that's terrifying. So let's take the gentler approach. Let's say the Earth slows down over a few years, maybe a decade, and just comes to a gentle stop.
Yeah.
No supersonic winds, just a standstill.
Okay. So we survived the initial stop, but now we aren't spinning. Does the shape change?
The bulge.
The bulge. Remember that oblate spheroid shape? That 26-mile bulge at the equator is only there because of the centrifugal force pushing outward. If you take away the spin, gravity wins completely.
It just snaps back.
Over time, yeah. Gravity would pull the Earth back into a perfect sphere. The rock might take a while to settle. You'd have earthquakes and volcanoes on a scale we can't imagine as the crust readjusts. But the water would move immediately.
Where would it go?
The oceans are currently being held up at the equator by that spin. Without it, they would flow toward where gravity is strongest, which, on a perfect sphere, would be the poles, because they're now the lowest points relative to the center.
So the equator would dry up.
You would have a massive equatorial supercontinent emerging. The Atlantic and Pacific Oceans would drain away from the middle of the planet and pool at the North and South Poles. You'd essentially have two massive polar oceans and a single ring of land around the middle.
The map of the world would be unrecognizable. Continents we know would be gone or merged or half drowned.
Totally unrecognizable, and that's before we even talk about the climate. If we stop spinning the day-night cycle as we know it, it ends.
Right. Because if we are just sitting there, one side is facing the sun and the other is facing the dark, permanently.
Well, not necessarily permanently. The Earth would still be orbiting the sun, so a day would last a year. You would have 6 months of continuous baking sunlight and 6 months of absolute freezing darkness.
So the sunny side would essentially be a barbecue.
It would be unlivable. The temperature would skyrocket past the boiling point of water. The oceans on that side would evaporate, creating a thick, crushing, humid atmosphere, maybe triggering a runaway greenhouse effect like on Venus.
And the dark side?
The dark side would plummet to hundreds of degrees below zero. The atmosphere itself might freeze and fall as nitrogen snow.
So is there anywhere you could live? Anywhere at all?
There is one theoretical spot. It's called the Terminator line.
It sounds like a movie title.
It does, doesn't it? It's the twilight zone, the ring separating the light side from the dark side. In that thin strip, the sun would be perpetually on the horizon. It wouldn't be too hot or too cold. You would have perpetual dawn or dusk.
So humanity would be huddled in this one narrow band on the planet.
huddled in this pneumatic ring, probably constantly moving to stay in that sliver of twilight as the Earth makes its slow orbit around the sun. It's a terrifying, desperate image. We rely on that simple spin more than we could ever realize.
It's the engine of our climate and our geography. But let's get back to the shape for a moment, the shape as it is now. We talked about the hamburger shape. But Tyson has another analogy that just blew my mind, the cosmic cue ball.
Ah, yes. This is one of those facts that fundamentally changes your perspective on scale. It's a real paradigm shifter.
So we look at the Earth and we see massive mountains, deep trenches, grand canyons. To us, the Earth has this incredibly rugged, textured surface. If you climb a mountain, you feel that texture in your legs. It's real.
Right. If you run your hand over a Relier globe, the kind with the bumps on it in a classroom, the mountains feel like sharp spikes. The Himalayas are like a jagged scar.
But Tyson says that is a gross exaggeration.
Yeah.
He says, and I love this visual, if you had a super-duper jumbo gigantic finger,
His words.
if you had a giant finger and you dragged it across the surface of the Earth, oceans and all, it would feel as smooth as a cue ball.
It's so hard to believe, but the math checks out perfectly. Think about it. The distance from the bottom of the Marianas Trench, the deepest point on the planet, to the top of Mount Everest, the highest point, is about 12 miles.
Okay, 12 miles of vertical variance.
But the diameter of the Earth is 8,000 miles. So the roughness is a tiny, tiny fraction of the total size. It's negligible on a cosmic scale. If you shrank the Earth down to the size of an actual cue ball,
You wouldn't be able to feel the mountains or the trenches.
not at all. They'd be smaller than the microscopic imperfections in the cue ball surface. He says the Earth is smoother than any ball bearing legally allowed in a factory under international standards.
That makes me feel incredibly small. The highest point I can imagine climbing, the most arduous physical journey a human can take, is just a microscopic imperfection on a perfectly smooth sphere.
It's a lesson in perspective, isn't it? What feels massive and monumental to us is completely invisible to the universe.
So let's take that rotation and ramp it up for a second. We talked about Earth doing 1,000 miles per hour. Tyson compares this to pulsars to show us the absolute limits of physics.
Yes, this is where you enter the realm of extreme physics. Tyson brings up pulsars. These are neutron stars. And to get a neutron star, you have to imagine taking the mass of our sun, which is huge, it could fit 1,000,000 Earths inside it, and crushing it down until it's the size of Manhattan.
The mass of the sun and the size of a city, the density there must be insane.
It's staggering. A single teaspoon of neutron star material would weigh 1,000,000,000 tons. And these things, they preserve their angular momentum from the original star. When they collapse, they spin up, like an ice skater pulling in their arms to spin fast.
Well, that's faster.
A lot faster. Some of them rotate up to 1,000 times per second.
1,000 times a second. That doesn't even sound like rotation anymore.
Yeah.
That just sounds like a hum.
A vibration.
It essentially is. But here's the limit of reality, the cosmic speed limit. Tyson explains that there is a hard ceiling on this. If they spun much faster, say around 4,500 revolutions per second, the equator of the star would be moving at the speed of light.
And since nothing with mass can move at or faster than the speed of light,
The star would fly apart. Matter would literally dissolve into energy or just be flung into the void. The forces holding it together would fail. So, rotation isn't just about making us a little chubby around the equator. It's a fundamental limit on how matter can exist. If you spin too fast, the universe forbids you from holding together.
okay, so we have established that our solid ground is actually a smooth, spinning, slightly squashed ball that is constantly fighting to not fly apart. But let's talk about the glue. Let's talk about what keeps us stuck to it. Gravity.
Gravity, the invisible tether. Or so we used to think.
This is where we get into Brian Greene and Stephen Hawking, because I think most of us, thanks to high school physics, we have this Isaac Newton view of gravity. It's the apple falling on the head.
Right. The Newtonian view is very intuitive. It makes sense to our brains. Newton described gravity as a force, an invisible hand, or a rope that connects two objects. The Earth pulls on the moon, the sun pulls on the Earth. It's a tug of war across empty space.
And to be fair to Newton, that math works really, really well. It gets us to the moon. It allows us to build bridges and predict tides.
It works for low speeds and moderate gravity. It's a fantastic approximation. But it started to break down when astronomers looked very closely at the orbit of Mercury. Mercury wasn't moving right. It was wobbling, precessing, in a way Newton's equations couldn't explain.
There was a glitch in the matrix.
A tiny one, but a persistent one. And then Einstein came along and said, no, 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 you're looking at it all wrong. It's not a force.
Right. This is where he completely changed the game. Einstein revolutionized our understanding with general relativity. He said gravity isn't a force in the traditional sense. It's not a rope. It's a curvature. It's the warping of the fabric of space-time itself.
And this is where everyone's brain starts to hurt a little bit.
Yeah, this is the rubber sheet analogy, right? Both Hawking and Green use this to help us visualize it because it's so counterintuitive.
It's the classic visualization for a reason, even though it has its limits. So imagine a trampoline or a big stretch rubber sheet. It's flat. Now, you place a heavy bowling ball in the middle of it. That's our sun. What happens?
The sheet curves down. It creates a depression, a valley around the ball, a gravity well.
Exactly. Now, take a little marble, that's the Earth, and roll it along the sheet. If you roll it straight, it doesn't go in a straight line from an outside perspective. It curves around the bowling ball.
But not because the bowling ball is grabbing it with some invisible rope.
Precisely. There is no invisible rope. The marble is just trying to follow the straightest line it can along the curved surface. It's falling around the indentation. That is what an orbit is. We aren't being pulled by the sun. We are rolling along the valley that the sun has carved into the fabric of space.
That is such a trippy concept. Space isn't just an empty box we float in. It's a fabric that bends. It has topography. It has hills and valleys.
And we are all just rolling around in it. Brian Greene takes this a step further with his tornado ride analogy to explain the geometry of this. He wants us to understand that because space is curved, the rules of geometry we learned in school, Euclidean geometry, actually break down.
Okay, so imagine one of those carnival rides that spins really fast. The rotor or the gravitron where the floor drops out and you stick to the wall because of the centrifugal force.
Right. Greene asks us to imagine taking out a ruler. If you measure the circumference of that ride while it's stationary, it's standard high school geometry. Circumference equals pi times diameter. Simple, it works.
But then you spin it up, close to the speed of light.
When you spin it, special relativity kicks in. Objects in motion experience a contraction in the direction of motion. It's called Lorentz contraction. The rulers that you place along the spinning edge would effectively shrink. So if you measure the circumference while it's spinning, you fit more of these shrunken rulers around the edge.
But the rulers measuring the diameter going across the middle, they aren't moving in the direction of their length, so they don't shrink.
They don't shrink. So suddenly your circumference seems longer, but your diameter is the same. The ratio changes. Pi is no longer pi. The geometry itself has been warped by the motion.
That's wild.
And Greene explains that if you draw a circle on a flat sheet of paper, the circumference is pi times the diameter. But if you draw it on a sphere, like a basketball, the circumference is actually less than what the formula predicts for that diameter. And if you draw it on a saddle shape, which curves essentially in and out at the same time, the circumference is more.
And Green's point is that gravity does this to space itself. It's not flat.
Precisely. A massive object like the sun warps space so that the geometry is no longer flat Euclidean geometry. We are living in a non-Euclidean universe. The shortest distance between 2 points isn't always a straight line. Sometimes it's a curve, because the space itself is curved. That's what airplanes do with their flight paths, following the curve of the Earth.
It's not just space, though. This is the part of the deep dive that always gives me a headache. Gravity warps time.
It does. They're inextricably linked. Space and time are a single fabric space-time. You can't warp one without the other. Greene uses the story of George and Gracie to explain this.
Our intrepid astronauts.
So imagine George and Gracie are in a spaceship far from any planets or stars. They synchronize their clocks perfectly, down to the nanosecond. Then George gets on a long cable and lowers himself down toward a massive object, let's say the sun, or even a black hole. He hangs out there for a while, closer to the strong gravity source, while Gracie stays far away in open space.
And when he climbs back up to the ship and they compare watches?
His clock will be behind Gracie's. Less time will have passed for him. He will be slightly younger than her.
Because gravity literally slows down time.
Yes. The stronger the gravitational field, the slower time moves relative to someone in a weaker field.
So wait a minute. If I live in a basement apartment, am I aging slower than someone who lives in a penthouse on the 80th floor?
Theoretically, yes. Because you are closer to the center of the Earth's mass, gravity is infinitesimally stronger for you.
I knew there was a benefit to the basement. I'm saving nanoseconds a year.
We're talking incredibly tiny fractions of a second over a lifetime, but yes. This isn't just theory, by the way. This is proven applied physics. We have to correct for this with our GPS satellites.
How so?
The satellites are orbiting far above the Earth, so they feel less gravity than we do. Their internal clocks run faster than the clocks in our phones on the ground. They also run slower because of their high speed. That's special relativity. But the general relativity effect from gravity is much stronger. If the engineers didn't program Einstein's equations into the GPS system to account for this time difference,
The whole system would fail.
the navigation would drift by miles every single day. Your phone would tell you your house is in the next town over.
That is wild. We're using general relativity to find the nearest Starbucks.
It's concrete proof that we are living in a dynamic, warping, four-dimensional fabric. We aren't just on the ground. We are riding a wave in space-time.
Okay, let's take a breath. Space is curved, time is flexible, and the ground is a smooth cue ball. Let's bring it back to something a bit more visceral. Let's talk about breathing.
Breathing is good. I highly recommend it.
We are spinning through a vacuum. Space is cold, dark, and airless. And yet, we're sitting here comfortably. Tyson calls this the Goldilocks zone.
It's a term astronomers use a lot. We are in the habitable zone, and it's purely a function of our distance from our star. If Earth were much closer to the sun, our oceans would boil away into steam. All water would be vapor.
And if we were farther out?
They would freeze solid. The entire planet would be a ball of ice. We are in that narrow, precious band where the sun's energy is just right for liquid water to exist on the surface.
But Sagan points out in Cosmos that just right is a fragile state. It's not a guarantee. And he points to our neighbor, Venus, as a terrifying warning sign. Venus is often called Earth's twin, right, in terms of its size.
In terms of size and mass, yes, they're very similar. But Venus is the stuff of nightmares. Sagan describes it vividly. It's effectively a planet-wide catastrophe. The surface temperature is roughly 900 degrees Fahrenheit, hot enough to melt lead.
Melt lead.
And the atmospheric pressure is 90 times that of Earth. Standing on the surface of Venus would feel like being a kilometer underwater, but in an oven.
And the really scary part is, Venus and Earth probably started out pretty similar, so what went so horribly wrong?
The runaway greenhouse effect. This is key to understanding our own climate's fragility. Sagan explains that Venus has a massive, thick atmosphere made almost entirely of carbon dioxide. Sunlight gets in, hits the surface, and tries to bounce back out into space as heat, as infrared radiation.
But the CO2 acts like a heavy blanket.
The heaviest blanket imaginable. It won't let that heat escape, so it just builds and builds and builds over millions of years until the planet is a pressure cooker.
And here's the kicker. Sagan notes that Earth has just as much carbon as Venus.
Right.
We aren't chemically that different in our total inventory.
We do. It's a shocking fact. But ours is locked away. It's in the rocks. It's in limestone, chalk, marble. It's in the shells of sea creatures that became those rocks. It's solid. It's sequestered.
So the danger, and Sagan is very specific and prescient about this, is that if we heat up the Earth too much, we could start releasing that locked-up carbon from its geological prism.
Exactly. It's a positive feedback loop. If you heat the oceans, they release dissolved CO2. That CO2 causes more warming, which can then release more CO2 from the permafrost and maybe even the rocks themselves. That is the runaway part. Once it passes a certain tipping point, you might not be able to stop it until Earth looks like Venus.
That is a terrifying thought. Venus is the hot death, but then you have Mars on the other side, the cold death.
Mars is what happens when you lose your atmospheric blanket.
Yeah.
It's a frozen desert. It's too small, its gravity's too weak, and it lost its magnetic field, so the solar wind just stripped its atmosphere away over billions of years.
But Sagan brings up a fascinating concept here, which I think is so hopeful. Terraforming.
This sounded like pure science fiction when I first read it in Cosmos, but he treats it as a legitimate, long-term engineering problem. How do we fix Mars? How do we bring it back to life?
And how do we do that? We can't just ship an atmosphere over.
No, but Mars has one locked away. He suggests a really ingenious, albeit massive, project. Mars has polar ice caps. But they aren't just water ice. They have huge amounts of frozen carbon dioxide dry ice. Sagan asks, what if we could melt them?
With giant space heaters.
Something a bit more subtle. He suggests changing the albedo, the reflectivity of the caps. Dark surfaces absorb heat, light surfaces reflect it. Mars ice caps are white and reflective. If we could somehow dust them with a dark powder.
Like coal dust or something.
Or pulverize dark rock from its moons. Or And this is the beautiful biological solution. Maybe we could genetically engineer very dark plants like lichens that can survive the extreme cold. The idea is to darken the ice caps so they absorb more sunlight.
And if they absorb heat,
The CO2 ice sublimates. It turns directly from a solid into a gas. That gas thickens the atmosphere. A thicker CO2 atmosphere creates a greenhouse effect, which warms the planet a little, which melts more ice, which thickens the atmosphere more. Another feedback loop, but a positive one this time.
and suddenly you have a blue sky on Mars.
It would take hundreds or maybe thousands of years, but the physics is sound. We could potentially wake up a dead world. It's the inverse of the Venus problem.
Speaking of waking up worlds, let's look at where our own atmosphere came from. Because it wasn't always this nice, breathable mix. Tyson and Lewis Dartnell both mentioned this, that something like 99% of our atmosphere is of biological origin.
This is one of my absolute favorite facts because it connects geology and biology so perfectly. The sky isn't just a backdrop for life. The sky is made by life.
The sky is made by life. That's a great line.
Early Earth had virtually no oxygen in its atmosphere. It was a toxic soup of methane, ammonia, carbon dioxide. Complex life like us couldn't exist. Then, about 2.5 billion years ago, these little microscopic heroes showed up. Cyanobacteria, blue-green algae.
The first photosynthesizers.
Right, and they were anaerobic, which means they didn't need oxygen. In fact, oxygen was a deadly poison to them. It was their waste product. They spent a billion years just sitting in the ocean, taking in sunlight and CO2, and pumping out oxygen as a waste gas.
So the air we breathe, the thing that keeps every one of us alive, is basically ancient bacteria poop.
In a manner of speaking, yes. They polluted their own world with this toxic oxygen. It caused a mass extinction for most of the anaerobic life on the planet, but it unwittingly terraformed the planet for us. They created the ozone layer, they cleared the sky of methane haze. We are living in the aftermath of their global pollution event.
That puts a different spin on taking a breath of fresh air. You're inhaling the industrial exhaust of ancient algae.
It just shows how powerful life is as a geological force. Life didn't just adapt to the planet, life changed the chemical composition of the entire atmosphere.
Okay, so we've covered the rock, the gravity, and the air. Now let's look outward. Because Sagan has this incredible ability to imagine life in places where we think it shouldn't exist. We tend to have a real bias, don't we? We look for Earth 2.0.
We do. We're very parochial. We look for rocky ground, liquid water, and oxygen-rich atmosphere. But Sagan challenges us to look at the gas giants, Jupiter and Saturn.
Now, usually when we think of Jupiter, we think hostile. It's the definition of hostile. It doesn't have a surface. It's just gas that gets denser and denser and hotter until it turns into a bizarre, metallic liquid hydrogen. There's no ground to stand on.
So how could life possibly exist there? Sagan, along with the physicist E. Salpeter, came up with a rigorous thought experiment. They didn't just wave their hands, they did the math. They asked, if the physics forbids walking, what does it allow?
Floating.
Exactly. If you can't walk on the ground, you have to float in the atmosphere. They imagined creatures they called floaters.
Describe these. This is one of the coolest parts of Cosmos.
Imagine giant living balloons. Vast organisms, maybe kilometers across, the size of cities.
City-sized biological balloons. Just drifting.
They would have to be that huge to hold enough light gas-like heated hydrogen or helium, which they'd generate metabolically, to stay buoyant in Jupiter's atmosphere. They'd float in the upper layers, soaking up sunlight or feeding on complex organic molecules that are known to be generated by the constant lightning storms there. They'd be like giant drifting jellyfish in a sky ocean.
And since they are floating, they are part of an ecosystem. They aren't alone.
Right. Sagan introduces the other players in this hypothetical drama, the hunters.
The predators.
Evolution almost always creates predators. These would be fast, maneuverable creatures. They wouldn't need to be buoyant, just aerodynamic. Perhaps they'd be jet-propelled by expelling gas, and they would hunt the big, slow floaters for their organic molecules and their reservoirs of pure hydrogen.
It's like a cosmic Serengeti in the clouds. Whales and sharks, but in the sky.
And then beneath them all, you have the sinkers. The microscopic life that fails to stay aloft and slowly, over generations, drifts down into the crushing hot depths of the planet to be destroyed. It's a full cycle of life, completely independent of solid ground.
It's so vivid, isn't it? It completely challenges our bias. We think life needs a sidewalk. Sagan says life just needs an energy gradient in chemistry.
And it highlights that habitability is a physics and chemistry problem, not just a geography problem. If you have energy and carbon, life might just find a way.
Speaking of other worlds, We have to mention Titan, Saturn's largest moon. This was another of Sagan's great obsessions.
Titan is one of the most fascinating places in the solar system. It's the only moon that we know of that has a thick, dense atmosphere. Thicker than Earth's, actually.
But it's not air. You definitely can't breathe it.
No, it's mostly nitrogen, like our air, but also a lot of methane. And it's cold. Really, really cold. About minus 290 degrees Fahrenheit. But the surface is covered in what Sagan calls organic sludge.
Sounds appetizing.
It's a substance called tholins. It's complex hydrocarbons formed by sunlight hitting the methane in the atmosphere. It's the building blocks of life. It's raining liquid methane on Titan. There are methane lakes and rivers and seas.
Well, it's like a bizarro Earth.
Exactly. Sagan's point was that even though it's freezing, all the necessary chemistry is there. He used the wonderful phrase, life is merely possible.
Merely possible. I love that. It's cautious, but it's so hopeful.
It reminds us that our definition of normal is very narrow. On Titan, water is as hard as rock, and methane is the liquid that carves canyons. Maybe something swims in those methane seas. We don't know.
So we have these potential worlds, Mars, Titan, the clouds of Jupiter. And that brings us to the inevitable final question. What happens to this world? What is the fate of the Earth?
Well, if we look at the long timeline, the solar timeline, it's a bit somber. It's a definite end date.
The sun isn't a forever battery.
No. Stars evolve. They have a life cycle. Our sun is a stable, middle-aged star right now, but it's slowly getting hotter and brighter. In about 1 billion years, it will be so hot that Earth's oceans will boil away, and that's the end of complex life. But the real show starts in about 5 billion years.
That's when it runs out of fuel.
It will run out of hydrogen fuel in its core, and it will swell up, expanding into a red giant.
And that's the end of the Goldilocks zone.
Sagan writes beautifully and terrifyingly about this. He predicts a last perfect day on Earth.
A last perfect day.
As the sun expands, it will swallow Mercury and Venus. For Earth, the sky will fill with this giant red angry star. The oceans will boil, the atmosphere will be stripped away into space, the surface of the rock itself will melt, the Earth will be scorched to a cinder. It is inexorable. Solar evolution doesn't care about our real estate values or our borders.
But that's billions of years away.
Yeah.
We have more immediate problems, don't we? The human variable.
We do. We are perturbing the system right now. We talked about Venus and the greenhouse effect. We are currently conducting an uncontrolled experiment on our own atmosphere, releasing the carbon that the Earth spent hundreds of millions of years locking away.
But it's not just us, right?
Yeah.
Louis Dartnell points out that the Earth itself is constantly shifting under our feet. Plate tectonics.
Right. We think of the map as static, but the continents are rafts floating on a sea of magma. They've crashed together to form supercontinents and pulled apart dozens of times. Dartnell connects this to human evolution in a way I hadn't thought of before.
How so? What's the connection?
He argues that the very shifting of the crust may have created us. Specifically, the formation of the Great Rift Valley in East Africa. As the tectonic plates pulled apart, it created a unique and unstable landscape that fluctuated wildly between dense forest and open savanna, wet seasons and dry seasons.
It was unpredictable.
And that instability, that constant change, forced our primate ancestors to adapt. They couldn't just stay in the trees kept disappearing. They had to come down, walk upright to see over the tall grass, and develop big, problem-solving brains to survive. We are a product of this planet's geological instability.
So the wobbly ground and shifting continents actually made us human.
In a very direct way, yes. We are children of plate tectonics.
Which brings us full circle to Sagan's pale blue dot. We are the only species on this planet that knows any of this. The dinosaurs didn't know about the asteroid. The cyanobacteria didn't know they were terraforming. We know.
And that is Sagan's ultimate philosophy. We are the only species capable of understanding our own potential demise and therefore potentially preventing it or moving beyond it.
He suggests that our destiny might be to leave.
If we survive the technological adolescence of our civilization, that's the great filter theory. If we don't turn Earth into Venus with our carbon or destroy ourselves in some other way, we might one day head for the stars. Maybe to Mars to begin the long work of terraforming it, maybe to build habitats in the clouds of Venus.
Or maybe we'll genetically engineer ourselves to be floaters on Jupiter.
Who knows? The physics allows for incredible possibilities. The universe is vast, and we have barely left the front porch.
It really is a profound perspective shift. You start this deep dive thinking about the ground as just dirt and rock, you ended realizing you were strapped to the outside of a spaceship.
A very complex, self-regulating spaceship that is maintaining a delicate atmospheric balance, spinning just fast enough to squash itself but not fly apart, while surfing a deep gravity well around a giant nuclear fireball.
So what does this all mean for the listener? We've covered a lot of heavy physics. What's the takeaway?
I think it means we need to respect the mechanism. We tend to think of the environment as a beautiful backdrop to our human drama, but it's not. It's a machine. It's a physical, chemical, biological machine with breaking points. Venus broke, Mars broke, Earth is working, for now.
And we are the mechanics who just woke up in the engine room.
And we're holding a wrench, trying to figure out what all the dials mean before the pressure gauge gets too high.
I love that. And I want to leave the listener with this final thought from both Tyson and Sagan. We talked about the shapes, the gravity, the gas, but ultimately, what are we made of?
Stardust.
Stardust.
It sounds like a line from a song, but it's literal, fundamental astrophysics. The Big Bang only created the lightest elements, hydrogen and helium, and a little lithium. But you are made of carbon, nitrogen, oxygen, iron in your blood.
So where did all that come from?
It was cooked in the hearts of dying stars. Stars that lived and died billions of years before the Earth or the Sun were even formed. They fused those heavier elements in their thermonuclear cores, and then, in their death throes, they exploded as supernovae, scattering that enriched dust across the galaxy. The cloud that formed our solar system was the recycled debris of those dead stars.
So every atom in my hand, in my body,
was once inside a star. We aren't just on the Earth, we are the Earth. We are chemically connected to all other life and atomically connected to the entire cosmos. We are the part of the spinning blue marble that stood up and started asking questions.
we are the universe experiencing itself.
Precisely.
So next time you are walking down the street and the ground feels solid and stationary beneath your feet, just remember, it's not flat, it's not still, and it is the only thing protecting you from the endless freezing vacuum of space.
Try not to get dizzy.
Thanks for joining us on The Deep Dive. We'll see you out there.